Seismic acquisition geometries and seismic data. Here is one of the key references used to develop this class. In the previous lectures, our objective was to familiarize you with the phenomena of wave propagation and with the physical laws which govern seismic wave propagation, namely the elastic wave theory. We do not have access to snapshots of wave propagation in the Earth. We are limited to data from sensors on or just below the surface of the Earth, or in boreholes. So we have to make sure that sensors effectively measure the desired physical quantities and that they are adequately distributed. That is the task of seismic data acquisition. Our objective is to describe the current and emerging distributions of source and receivers, that is, seismic acquisition geometries, in seismic experiments. We will also describe seismic data associated with these acquisition geometries. Some of the key outcomes are understanding the differences between marine towed streamer acquisition and ocean bottom acquisition, understanding differences between marine and land acquisitions, understanding the difference between primaries, free surface multiples, and internal multiples, understanding the difference between ghost and multiples, understanding the differences between shot, receiver, midpoint, and offset gathers. Familiarizing yourself with the reciprocity theorem for towed streamer acquisition. The surface of the Earth is either solid or covered by water. So as a seismic acquisition is mostly carried out on the surface of the Earth, it is important that we start by a review of seismic acquisition in both water and solids. The concept of homogeneity, heterogeneity, acousticity, and elasticity controls the type of waves that we can generate and the physical quantities that we can record. Therefore, their implications for seismic acquisitions are profound. For instance, the division of seismic experiments into land and marine is primarily related to the fact that 1, in marine cases, the acquisition is conducted in water, which can be treated as acoustic and homogeneous, whereas 2, in land cases, the acquisition is conducted in heterogeneous elastic media. Actually, the differences between the various acquisition scenarios presented here come down to the difference between generating and recording waves in a homogeneous fluid and in a heterogeneous elastic medium, or solid. The fluid is generally considered homogeneous, with a relatively flat air-water interface. It supports only P waves, and both pressure variations and particle velocity can be recorded. The solid is generally considered a heterogeneous elastic medium, with a non-flat air-solid interface at the Earth's surface or a non-flat water-solid interface at the sea floor. It supports P and S waves, and the 3 components of particle velocity can be recorded. On the sea floor, pressure can be recorded in addition to the particle velocity. Here we are showing seismic response to the velocity variations with depth in the Atlantic Ocean in the summer. Notice that these velocity variations are quite small. We also show the response of the equivalent homogeneous velocity. So as far as seismic waves are concerned, oceans can be treated as homogeneous media because the seismic response of the homogeneous sea is almost identical to that of heterogeneous sea. There are several configurations of source and receiver distributions in the sea. The ones commonly used for petroleum exploration and production are 1. The towed streamer experiment, in which sources and receivers are distributed horizontally in the water column near the sea surface. 2. The ocean bottom seismic experiment, or OBS experiment, in which the sources are in the water column and the receivers are at the sea floor. 3. The vertical cable experiment, in which the sources are in the water near the sea surface, just like in towed streamer and OBS experiments, except that receivers are distributed in the water in the form of a vertical array. And 5. The walkaway VSP, or vertical seismic profile experiment, in which the sources are in the water, just as in the previous experiment, but with receivers inside a borehole. We will describe these acquisition geometries in detail in these lectures. Let's continue with examples of seismic acquisition in solids. On land, the commonly used source and receiver distributions are as follows. The surface seismic experiment, in which sources and receiver are at the surface of the Earth, or just a couple of meters, generally less than 10 meters, below the Earth's surface. The vertical cable experiment consists of sources at the surface, or near the surface of the Earth. The receivers are distributed inside boreholes, which are generally less than 500 meters deep. The family of VSP experiments consists of experiments in which the source is at the Earth's surface, and the receivers are inside a borehole, or vice versa. The borehole, in the case of the VSP experiment, is generally as deep as the targeted petroleum reservoir. Again, we will describe these acquisition geometries in detail in this lecture. There are cases such as continental margins, or mud, which cannot be clearly defined as marine or land. They are called transition zones. We will also discuss how seismic experiments are conducted in these cases. The picture here summarizes these three cases, that is, land, marine, and transition zones. Let's now describe one of the marine acquisition geometries, that is, towed streamer acquisition. We have divided our description of towed streamer seismics into 7 subsections. We will start with the distribution of source and receivers. Here is towed streamer acquisition, in which a ship is towing a set of cables containing receivers to record signals generated by seismic sources as the vessel maneuvers across potential petroleum reservoirs. These cables of receivers, generally called streamers, are towed at a depth of between 5 to 50 meters below the sea surface. A typical streamer today is 5,000 meters to 10,000 meters long. It carries several hundred sensors, known as hydrophones, which record pressure changes. In conventional acquisition, each seismic receiver is composed of 12 to 24 hydrophones, which are summed before or after recording, depending on the processing objectives. The spacing between receivers, that is, the center of a group of hydrophones, is generally 12.5 meters. Typical acquisition vessels today can tow 12 to 32 streamers spaced 50 to 100 meters apart. Towed streamer acquisitions are generally performed as a series of parallel shooting lines, The lines shot during the survey are called inline sections, or rows. Lines perpendicular to these lines are called cross-line sections, or columns. The cross lines can be generated from inline data. One of the major challenges with towed streamers is maintaining constant streamer spacing. Present seismic data processing requires that the data be uniformly sampled in space. That is why the distance between streamers must be constant. Currents, tides, and other forces can cause streamers to feather or drift laterally from program positions, and in extreme cases, they get tangled. Tangled streamers have to be reeled back to the vessels and untangled manually, resulting in non-productive time. Several types of sources can be used in towed streamer acquisition. The most common source involves an array of airguns, which operates as an exploding source. Like the receivers, the typical seismic source is an array composed of subarrays, each containing up to 6 airguns about 3 meters apart. Now, let's talk about marine seismic source, which is typically an array of airguns. The airgun arrays are generally towed at a depth of 5 to 50 meters, but they are usually located above the streamers. Here is an example of a marine 18 airgun array configuration without streamers. In summary, here are the main characteristics of towed streamer acquisition. 1. Sources and receivers are in the water. Therefore, the sources generate only P waves, and the physical quantity recorded is the pressure. That is, the acceleration of the fluid medium. The sensor used to make pressure measurements in the water are known as hydrophones. 2. Because pressure is non-directional, a hydrophone's output is independent of wave direction. Assuming that the patterns of hydrophones are isotropic, this precision is important, because remember that we are dealing with an array of hydrophones in opposed to a single hydrophone for each receiver. And 3. The particle velocity can also be recorded. Let's move on to 4. Towed streamer acquisition is a roll-along experiment. That is, after each shot, the lines of receivers are moved to another appropriate location, and the source is fired again. 5. The configuration of sources and receivers is called off-in spread. This means that all the receivers are on one side of the shot point. 6. The assumption that seismic sources are point sources is realistic for petroleum seismology studies, despite our usage of arrays, because they generally act on very small volumes. And finally, 7. Another major problem with towed streamer acquisition is that the spacing between streamers is very large. Remember that we consider the streamer directions, that is, the X direction to be the inline direction and the Y direction to be the cross-line direction. We are now going to expand on the discussion of airguns, in particular oscillations, associated with the airgun source, known as bubble oscillations. As we pointed out earlier, the airgun is the most commonly used source mechanical device in marine surveys. It includes a chamber of compressed air and releases a high-pressure bubble of air into the surrounding water as a source of energy to generate P waves. Because the pressure inside the bubble greatly exceeds the hydrostatic or external pressure, the pressure of bubbles causes variations in the pressure in the water as a function of time. These variations in the water pressure represent the airgun signature. Here we show underwater photographs of the bubble upon release of the air from the airgun. This lab experiment was carried out in a tank of water. We can see that the bubble has a nearly spherical shape after a couple of milliseconds. The bubble maintains this shape throughout its subsequent motion. That is why we generally treat the bubble as a sphere of air. The photo shown at the top left is a single air gun, and to the top right are 3 air gun clusters. At the bottom are pictures of air bubbles of 1 millisecond, of 1.5 milliseconds, and of 7 milliseconds after firing a small air gun in a water tank. Let's now look at the signature of air guns. We're going to use the words near field signature and far field signature. Near field signature corresponds to the case in which the distance between source and hydrophone is very small compared to the wavelength of wave propagation in the water. In other words, the hydrophone is close to the source, or about 30 meters from the source, or within the wavelength from the source. By contrast, the far field signature corresponds to the case in which the distance between the source and the receiver are greater than the wavelength of wave propagation in the water. Typically, the hydrophone is farther away from the source by more than 60 meters or more than 2 wavelengths. We can see in this near field hydrophone signature that the pressure in water peaks, then falls below the hydrostatic pressure, and then increases again above the hydrostatic pressure. In other words, the bubble oscillates. The amplitudes of these bubble oscillations are damped down with increasing time. The initial release produces the highest amplitude, and after that, the pressure amplitude and period decrease with time. The simultaneous processes of bubble expansion and bubble collapse is the reason of bubble oscillations with damping amplitudes. Basically, the air bubble released in the water by the air gun expands well beyond the point at which the internal and hydrostatic pressures are equal. When the expansion ceases, the internal bubble pressure is below the hydrostatic pressure, so the bubble starts to collapse. The collapse overshoots the equilibrium position, and the cycle starts once again. The bubble continues to oscillate with a period typically in the range of tens to hundreds of milliseconds. The airgun signature is essentially characterized by 2 parameters: the strength of its first peak and the period of bubble oscillation. These parameters vary with the volume of air in the bubble and the pressure at which the airgun is operated. Let's repeat this due to its importance. The airgun signature is essentially characterized by 2 parameters: the strength of its first peak and the period of bubble oscillation. These parameters vary with the volume of air in the bubble and the pressure at which the airgun is operated. The pressure peak increases with increasing airgun volume, and the bubble oscillations decrease with increasing airgun volume. But the bubble period does not increase in proportion to the pressure increase, because the pressure increases with water depths. The variations in the parameters of the airgun signature with pressure hold if we use water depths instead of pressure. The typical volumes of individual airguns used in E&P industry are between 20 and 100 cubic inches. The blue curves in this picture show the signatures of airguns with volumes between 40 and 250 cubic inches. In earthquake seismology, especially refraction, this volume can go up to 2,000 cubic inches. Ideally, we would like to have airgun signatures with one pressure peak only, that is, without oscillations of the water pressure. A significant attenuation of the oscillations in the airgun signatures can be achieved by firing several airguns of different volumes simultaneously, instead of firing a single airgun. The basic idea is that by adding several airgun signatures through the superposition principle, we build up the amplitude of the pressure peak, while the subsequent peaks cancel out because they are out of phase. The red curve here shows the result of the superpositions. The difference in the secondary peaks of the airgun signatures is due to the fact that the oscillations vary with the volume airgun. Here we illustrate this point. This figure shows the far-field signature of 6 airguns with different volumes. They are fired individually, and then all airguns are fired simultaneously. The far-field signature of an array of airguns looks quite different from a single airgun with less oscillation. The residual oscillation at around 300 milliseconds can be eliminated by using the debubbling techniques. Again, the signature in red is obtained when the 6 guns are fired simultaneously. Seismic data is generally represented or imaged as a sequence of shot gathers, receiver gathers, midpoint gathers, or offset gathers. What we will do next is describe shot and receiver gathers. Let's now analyze the different patterns contained in towed streamer seismic data. First, we will be analyzing data corresponding to a simple model made of 2 layers and a half space. Our analysis of the data corresponding to this model is based on snapshots of wave propagation, on seismic data themselves, and on a ray path description of patterns contained in this data. For clarity, the schematic diagram of ray paths generally ignores Snell's law. Here is the difference between drawing wave paths with and without the effects of Snell's law. Actually, it is a common practice in petroleum seismology to draw ray paths without using Snell's law. Except when stated otherwise, these simplifications of ray paths are limited only to our drawings. In other words, our data include the effects of Snell's law. The patterns in seismic data are generally described with the concept of event. An event is formed by coherent seismic energy corresponding to one of the wave types that has traveled from source to receiver via some path through the subsurface. The events can be grouped into direct waves, primaries, source ghosts, receiver ghosts, free surface multiples, and internal multiples. Again, the events in seismics can be grouped into 6 categories: direct waves, primaries, source ghost, receiver ghost, free surface multiples, and internal multiples. Let's elaborate on each of these categories. The expanding energy that moves from the source point to the receiver without hitting any interface is a direct wave. The snapshot at 150 milliseconds here show direct waves being recorded at some stations. Energy that travels upward to the free surface is reflected downward at the free surface and generates a new seismic event called a source ghost. A snapshot at 350 milliseconds shows source ghosts of direct wave. In conventional marine towed streamer acquisition, source and receivers are located in a water column near the sea surface. To clearly identify the various patterns which are contained in these data corresponding to this acquisition geometry, we consider the case in which source and receivers are located at 225 meters and 275 meters respectively in the water column. Here we are showing seismic data to the left and the ray paths of some of the events in these seismic data to the right. D here stands for direct wave. The direct wave has a linear move out when sources and receivers are at almost the same depth, as you can see in seismic data. Here, SGD stands for source ghost of direct wave. Primaries are seismic events which reflect or diffract only once in the subsurface before being recorded. Let's repeat this, it's very important. Primaries are seismic events which reflect or diffract only once in the subsurface before being recorded. P1 is a primary. It has reflected only once from the source to the receivers. Note that most present seismic imaging schemes assume that data contain primaries only. In other words, they require that direct, ghost, and multiple events, which we will introduce later, must be removed from the data before imaging. Let's repeat this important notion. Note that most present seismic imaging schemes assume that data contain primaries only. In other words, they require that direct, ghost, and multiple events, which we will introduce later, must be removed from the data before imaging. For this model, we have only two primaries, P1 and P2, because this model contains only two reflectors besides the sea surface, that is, free surface. Again, here we are showing seismic data to the left and the ray paths of some of the events in these seismic data to the right. P1 stands for primary. SGP1 stands for source ghost of primary P1. Events whose first bounce is at the free surface are source ghosts. There is a source ghost associated with each seismic event. Again, note that most present seismic imaging schemes assume that data contain primaries only. In other words, they require that direct, ghost, and multiple events must be removed from the data before imaging. Due to interferences between primaries and other events contained in the seismic data, the problem of removing multiples is one of the most challenging steps in seismic data processing, as we will see in future lectures. Receiver ghosts are events whose last bounce is at the free surface before being recorded. Here, RGP1 is the receiver ghost of primary P1. When the source is located above the receiver, there is no receiver ghost for direct waves. Otherwise, each event in seismic data has its receiver ghost. P2 is another primary. Here, RGP1 stands for receiver ghost of primary P1. RSGP1 stands for another receiver of P1. P2 stands for a second primary. SGP2 stands for source ghost of primary P2. RGP2 stands for receiver ghost of primary P2. RSGP2 stands for another receiver ghost of P2. So, free surface reflection events, that is, ghosts and free surface multiples, are events with at least one reflection at the sea surface. In theory, Present seismic imaging assumes that all of these seismic events are being removed from the data before imaging. Note that the snapshots shown in the previous slides do not contain any free surface multiples because they arrive late, that is, after 1 second, in which case snapshots become very complex due to the simultaneous occurrences of several reflections in transmissions, despite the relative simplicity of the model used in this example. However, the diagram of ray paths of events contained in these data allows us to picture the free surface multiples. Again, when the first and/or last reflection in the wave propagation path of a free surface reflection event is at the sea surface, the event is characterized as a ghost. All the other free surface reflection events are characterized as free surface multiples. Free surface multiples are generally distinguished by the number of bounces at the free surface. Free surface multiples, which include only one bounce at the free surface, are called first-order multiples. Free surface multiples which bounce twice at the free surface are called second-order multiples. Notice that each free surface multiple has its receiver and source ghosts. Here, M1 stands for free surface multiple. Internal multiples are seismic events with no reflection at the free surface, but with reflections between two interfaces other than the free surface. Compared to the primaries, the amplitudes of internal multiples are often quite small. One type of internal multiple that may be relevant is seafloor-related internal multiples, like the one illustrated here. Only the seafloor-related internal multiples with one bounce at the seafloor may be noticeable in towed streamer data. Now, let's consider the case in which source and receiver are very close to the sea surface. In other words, source and receivers here are located at 5 meters and 10 meters respectively in the water column. As illustrated here, the direct wave event interferes with the source ghost event when sources and receivers are at almost the same depth and at a very shallow depth. Notice that source ghosts, say of primaries, are almost indistinguishable from the primaries themselves when the sources are very close to the free surface, as they are in most marine experiments today. In conventional data processing, source ghosts are generally treated as a component of the source signature because they are indistinguishable from events associated with them. In other words, for each shot, a time-delayed reflection from the sea surface, or the source ghost, trails the seismic wave field traveling directly into the Earth from the shot. The interference of these two events can affect both low and high frequency information, as we will see later, and therefore the resolution of seismic imaging. Source ghost of direct waves is almost indistinguishable from the direct wave itself when the sources are very close to the free surface, as they are in most marine experiments today. Actually, all events interfere with source ghosts when sources are very shallow. These primaries interfere with the source and receiver ghost events here. Actually, all events interfere with their ghosts. These interferences can affect both low and high frequency information, and therefore the resolution of seismic imaging. Again, notice that source ghosts, say of primaries, are almost indistinguishable from the primaries themselves when the sources are very close to the free surface, as they are in most marine experiments today. In conventional data processing, source ghosts are generally treated as a component of the source signature because they are indistinguishable from events associated with them. Again, we notice that the receiver ghosts, say of primaries, are almost indistinguishable from the primaries when ZR is small. As we will see later, for some streamer depths, the amplitude of certain frequencies will be completely canceled at the recording sensor, that is, notches, and the amplitude of other frequencies will in fact be doubled. Again, internal multiples are seismic events with no bounce at the free surface, but with a bounce between two interfaces other than the free surface. This figure shows an example of internal multiples. Compared to the primaries, the amplitudes of internal multiples are often quite small, and they are sometimes hardly visible in seismic data. However, one type of internal multiple that may be relevant is seafloor-related internal multiples, like the one in this figure. Furthermore, only the first of the seafloor-related internal multiples, which bounce once at the seafloor, may be noticeable in towed streamer data. Here we show the simulated towed streamer data corresponding to the Pluto 1.5 model constructed by the Smart JV group. The model is shown in the corner. It includes 3 salt bodies. This model illustrates some of the deep water structures of the Gulf of Mexico. The model and the data are much more complicated than that in the previous example. We have indicated the direct wave, some of the primaries, and the free surface multiples included in these data. In practice, we cannot identify all primaries and multiples contained in the seismic data. We need computer codes to perform the task of going from our seismic data to the model of the subsurface. This task is known as seismic imaging. This task is known as seismic imaging. The field of reconstructing. Models from given data is broadly known as inverse problem theory. Seismic imaging is just a particular application of this theory. In summary, source ghosts, say of primaries, are almost indistinguishable from the primaries themselves when the sources are very close to the sea surface, as they are in most marine experiments today. In conventional data processing, source ghosts are generally treated as a component of the source signature because they are indistinguishable from events associated with them. We have now concluded our discussion of marine towed streamer seismics. When we return, we will talk about midpoint and offset gathers, out-of-plane reflections, and broadband seismics. Thank you for your attention.